Everything is clear? So far, so good? Don't be shy. If you have questions or something is not clear, just this is the time. Okay, so no questions. I think it's time to move into reference-free metrics. So now is your time, Sam.
Okay, so hi everyone. Luis, can you hear me?
Yes, I can hear you. And I think you should be able to have also control over the screen. If not, yeah, you should be able. Okay.
Okay, so yeah, thanks Luis for the detailed introduction of the dialog system in general and the reference-based matrix. So now let's dive into the reference-free matrix, which is try to address some of the problems that are encountered by the reference-based matrix. So by reference-free, we means that the input to the matrix is just the context as well as the hypothesis. So we don't do quality estimation based on the human written references. The first problem with the previous mentioned reference-based matrix is that they correlate poorly with the human evaluation. So as we can see here, on the right figure, when the human score of group 1 and the human score of group 2 actually have a perfect linear relationship. So there's one straight line in the figure, but as we can see, the blue score and the embedding average, their correlation with humans are actually very poor. So the dots are all completely random. So that's one problem with the reference-based matrix. So one cause of that is that because dialog systems for dialog generation tasks is like open-ended generation. So for one dialog context, there may be multiple semantically viable responses. So we need to, like, for reference-based matrix to work well, we need to write many semantic varying references, but that is very costly to obtain. And a second problem with the previous mentioned metrics are that they generally compute a similarity score, for example, between the reference and the hypothesis. This single score is kind of hard to interpret. It only captures the partially of the quality of the response. For example, the adequacy, or is kind of or whether the response is fluent. But there are many different dimensions with respect to the quality of the dialogue. So here we think that there is no one-size-fits-all solution to open domain dialogue evaluation. So we need to design different metrics to tackle one quality of the dialogue. Therefore, it is kind of necessary to rely on the reference-free metrics, or we call them context-dependent metrics. So actually, there are two. We can divide the reference-free matrix into two final groups. One is the untrained, the other is trained. So for untrained, it means that there is no model involved in. I mean, we do not train a model to score the response. We just rely on some heuristic method to compute a score. So one very common measure, reference-free measure, is the perplexity. So for perplexity, is basically used very popularly for evaluating the language model or the text generation task. It measures how well a probability model or the distribution predicts a sample. Here it may be a sequence of words. So in the case of dialogue generation, the input to the language model is basically the dialogue context, and we use perplexity to measure the likelihood of the generated response. So the lower the perplexity, we think the higher the conditional probability of the generated response. So it's commonly used in the literature to tune the model during the development phase. And another untrained metric is the thematic coherence. So it relies on the sentence embedding of the of the context and the hypothesis. So we try to compute a similarity between the hypothesis and the context. So it's a kind of coarse way of evaluating the local topical coherence. So it's like it works similarly for the reference-based metric as a embedding-based reference-based matrix. It's just we just replace the reference here with the embedding of the previous utterance of the current utterance. So the performance of this matrix actually largely rely on the encoder, the text encoder we used. So the better the semantic representation of the context and response, actually the better the performance will be. Then another way to realize this metric instead of using cosine similarity is to rely on a pre-trained NLI model to predict the entailment between the context and the response. So basically, that's the two metrics for the that are untrained reference matrix. Now we dive into the details of the end-to-end training-based reference matrix. This is kind of the current trend of the in open domain dialogue evaluation. So we rely on a model to score the dialogue or the dialogue response. So there are three actually important aspects that are relevant to the end-to-end training-based matrix. It's basically, the first one is self-supervision. Basically means that we don't rely on any human quality annotations to train the model. Instead, we just train a matrix on unlabeled, large-scale unlabeled human dialogue data. So in order for the self-supervision to work, we need to rely on some negative sampling strategies to construct negative samples, or we need to construct different negative samples so as to train the matrix to distinguish the positive sample from the negative ones. So here we can see an example here. We have the dialogue context, then we have the original ground truth response that is derived from the human-human conversation. Then we rely on the random utterance sampling strategies to obtain one response from a different dialogue. So we try to train a matrix that is able to tell the ground truth from the random response. This is just an example of the negative sampling. Of course, there are many different sampling strategies to improve the matrix performance. And third important aspect is the reliance on pre-trained language models. So as of now, the pre-trained language models are already like very common in the NLP applications. So for our end-to-end matrix, we just incorporate the model as part of the end-to-end pipeline to provide semantic representation of the input sequences. So it's kind of kind of common practice nowadays. So before diving into details of all different representative training-based metrics, we may first want to know the commonly used human dialogue corpus that we adopt to train the matrix. So basically, there are like four common domains that we use to train the matrix. One is the daily chit chat, which talk about the daily style like conversation, such as about hobby and life, everything. And the second domain is the knowledge grounded conversations. So basically means that the two people the two parties in the conversation will discuss topics that are grounded on the external documents, such as the Wikipedia page or some articles in the newspaper. And the third domain is the personal guided conversation. This means that there are two, like each speaker in the conversation, there is they will have a personal profile associated with the speaker. The personal profile means that it's a set of utterances that describe the hobbies, the personality of the speaker. So they try to engage in a conversation and introduce introduce themselves and discover some mutual interest. Then the last domain is the emotional dialogues, which means that the dialogue will discuss some emotional context. Then one speaker will like convey their emotions, emotional what they have been experienced, and then the other speaker will like act as a empathetic listener. So these are the 4 domains of the common used dialogue corpora. And here is just a list of statistics of the different representatives of dialogue corpora for each domain. So of course, for open domain dialogue research, there are like much more dialogue corpora than what we have been through, what I have go through just now. So actually, in GSTOR 2022, so the 7th Frederick Jennings Memorial Summer Workshop hosted by Johns Hopkins University, our team actually created a list of 18 dialogue datasets, open domain dialogue datasets. So we try to unify the format for easy processing, and we also provide additional annotations such as sentiment, and we translate the original English into other languages such as Spanish to facilitate multilingual research. So we also open source all the datasets in the GitHub link here. So as to facilitate maybe future research on open domain dialogue generation or evaluation, you may feel free to access this link here to get a copy of all the data sets. So now let's dive into the details of the training-based metrics. So the training-based metrics can also be categorized into turn level metrics and then dialogue level metrics. So by turn level metrics, we mean that the dialogue will only evaluate the quality of a single response. So by dialogue level metrics, we mean that we want to evaluate the quality of the dialogue, the multi-turn dialogue. So it's like a kind of a local evaluation method, local evaluation metrics versus a global evaluation metrics. So the first representative example of the turn level metrics is this Ruber reference and unreferenced metric blended evaluation routine published in IIII 2018. So the Ruber is basically is introduced to improve the reference component mentioned, the reference-based metric mentioned previously. They try to improve by introducing a unreferenced component. So the reference component is just rely on the computation of cosine similarity of sentence embeddings between the ground truth response and the generated response. It just measures the adequacy of the generated response. So it's kind of similar to what Luis mentioned previously. And the additional component is just the unreferenced part, whereby the authors trained a neural network to model the relevance of the generated response and the query response. So by query response, we mean that it's a query utterance which is the previous utterance within the current response. It means that, for example, I ask, how are you? Then the system may generate, I'm fine, thank you. So the query is, how are you? Then the generator response is, I'm fine, thank you. So this unreferenced scorer is basically a neural network of a simple two-layer feed-forward network with a sigmoid activation function after the output layer. So the model is basically trained in with the margin ranking loss. It is trained to give a higher scores to the ground truth replies than a random response from other different dialogues. Because previously we mentioned that the model will rely on some random sampling strategies. So we just to predict higher score for the ground truth and give a lower score to the random and the random dialogues. In this way, we can train a model to train a matrix in this manner. And after that, the score of both reference component and the reference-free component are combined to derive the single Ruber score of the response. So the author kind of observes that there is an increase in correlation with human evaluation by introducing the reference free component. So that's that early work of the reference free metric. So next is the representative example is the BERT-RuBER. So introduced in NAACL workshop 2019. So in 2019 actually is a kind of game-changing year for NLP. So the pre-trained language models based on bidirectional transformer encoders such as BERT and Robota actually completely changed the NLP field. So similarly for the open domain dialogue evaluation. So the author basically tried to improve the original, the previous mentioned RuBER with contextualized representation provided by the BERT encoder. So for the reference, for example, on the right, for the reference component, instead of using word-to-vec embedding, they just use a BERT encoder to provide a sentence level contextualized representation for both query and the response. Then they compute the cosine similarity of the embedding vectors of the response and the query. And for the unreferenced component, they modify the embedding layer. Originally, they use word-to-vec embedding. Then the authors just replace it with the BERT embedding. Then after that, use the max pooling operation to derive a sentence level vector representation. Then instead of using the margin ranking loss introduced in the original RuBER, they just replace it with an MLP classifier to perform the task. So the takeaway message of this representative example is that the contextualized representation provided by pre-trained language models such as BERT or Robota can actually indeed improve the metric correlation with human evaluation. Okay, so the third representative example is the MAUDI, which is so because the reference-free modeling of the RuBER and the BERT, they are kind of problematic because firstly they are designed for static evaluation. This means that they only evaluate the local contextual relevance of the context and the response. So if you recall in the previous slides on human evaluation, in the per turn evaluation setup, we would like to evaluate dialogues turn by turn in an interactive manner. But the RuBER and the BERT-RuBER are not designed to handle such situations. So in this ACL 2020 paper, they propose MAUDI to target evaluation in such a setup. So basically, compared to RuBER and the BERT-RuBER, which just simply use a random sampling strategy, the MAUDI actually also additionally propose use a variety of different sampling strategies that were introduced in the following slide. So firstly, let's look at the entire architecture of the MAUDI framework. So the input, as we can see on the right figure here, the input to the MAUDI framework is a sequence of utterances, and the output is a single scalar, indicating the quality of the current response. Here, that's a lot of money with respect to the entire context, which consists of the first 5 utterances. And we use the BERT encoder to map each utterances into an embedding representation. Then a max pooling function is used to convert all the sentence embedding vectors of different context utterances into a single context embedding vector. And then after that, we concatenate the context embedding vector and the response embedding vector, and use a feed-forward network is adopted after the then the concatenation vector concatenation is input into a feed-forward network, and the entire matrix is trained end-to-end with this lowest contrastive estimation loss. So in order to train the model, we need the original response like this, and also negative response that are obtained with negative sampling strategies that I will introduce in the next slide. So in this paper, the author proposed 2 categories of negative sampling strategies. One is the syntactic perturbation and the semantic perturbation. So for syntactic perturbation, so it's kind of, so we do text level manipulations of the response. just the current response. So it's within sentence perturbation. So such as the word order, like we shuffle the ordering of the word of the response, or we do that word drop, such as we randomly drop X% of the word in the response, such as 15% to 20%. Then we also do some word repeat operation, like we randomly repeat a span of words in the response. So in this way, we create a set of different negative samples with respect to the original human written response. And the second category is the semantic perturbation. So means that we change the meaning or change the meaning of the response, or we so for the one is the random utterance from another dialogue. So means that we pick a utterance that is completely irrelevant to the current context. Like if I ask how are you, then you reply me by give a reply like I just I ask you how are you, then you answer something like so like I'm studying, something like that. So it's topically irrelevant. So the second perturbation is utterance produced by a sequence model condition on the another dialogue context. So means that we sample, instead of randomly sample utterance, we just sample a random context from other dialogue, then use a sequence model to generate a response. So the response should be relevant to the other context instead of the current dialogue context. And the third one is similarly. So, but instead of using sequence model, we just use back translated model. We translate so we translate the utterance. So we first randomly sample utterance, then we translate them into English, from English to like Spanish or German, then we back translate them back to English. So it's like more introduce kind of both semantic and syntactic perturbations. So after that, so we try to assess the performance of the model. So to compare, actually to see whether it performs well, we can actually check the difference between the original response, the original response score given by MAUDI and the perturbed response score. So for the positive perturbations, like the semantic positive, so the difference should be as small as possible. And for the semantic negative perturbations, or syntactic negative perturbations, the score difference should be as large as possible. So this is to compare with the score given to the original response. So for example, for the back translated response or sequence generation, the score, the difference should not be very large. For example, for the back translation, so the MAUDI here just the score difference is just 0.07, but for the syntactic negative, such as word repeat, word order, the score difference with respect to the original response is kind of large, 0.8. So this showcases that it is able to tell the difference between the negative sample from positive samples. So then let's look at the fourth example, which is the USR. So as we can, the previous three metrics, previous two metrics, MAUDI and Ruber, they only focus on the contextual relevance of the response, which is only partially a partial quality. So we want to look into like multi-dimensionality of the response quality. So because the dialogue evaluation is actually multifaceted in nature. So this USR paper published in ACO 2020, they actually propose a set of different desirable properties of dialogue that we ought to evaluate at the turn level. So the first one is understandable. So it's like it evaluate whether the response is understandable in the context of the dialogue history. So basically the dialogue context. The naturalness of the response, so means that whether is more pertaining to the grammar of the response, which is because we know some sequence models tend to generate like not well-formed text. So we want to evaluate whether the text generated are well-formed in terms of English grammar. So the third one is maintains context. So that's a response serves as a valid continuation of the conversation history. And the fourth one is user's knowledge. So this means that whether the generated response is grounded under external knowledge, whether it's truthfully deliver the information that is covered in the external knowledge base. For example, just now we mentioned the data set, the topical chat. So that one can be used to evaluate to train models that specifically evaluate such dimension. And the last one, this fine-grained is interesting us. We will try to see whether the response is engaging, whether it is dull or not. And then finally, the overall quality, which is the overall impression of the utterance. And in the paper, the author first proposed construct a high quality data set that's called the USR data set, because in order to benchmark the metrics, we need some kind of human evaluation data sets to assess the validity of the metrics. We compute correlation between the metric score and the human score. So we need a data set. At that time, there are not many high quality human evaluation data sets. So that's one contribution of the paper. So the author basically sample 120 dialogue contexts from personal chat and the topical chat introduced earlier. So each we select 60 dialogue contexts from each data set. So for each context, then they adopt a different set of generative model to generate 6 different responses of varying quality. Some responses are good, some responses are not good. So then there are 6 dialogue researchers. They will annotate each context response pairs along the 6 fine-grained quality introduced previously, like understandable. Then they will score whether the response is understandable or not. So for the overall quality, then on a scale of 1 to 5, they will try to score their first impression of the response. And here on the right is basically a kind of example from personal chat. But if they want to sample for the sample context, they just sample, for example, the first 3 utterances maybe. Then they use a dialogue model to generate a response following these three contexts, three utterances. And for the dialogue quality, we usually use the inter-annotator agreement to tell whether the quality of the data sets are good or not. It observes that for each dimension, like here, there is a moderate to high inter-annotator agreement. So the quality of USR data set is kind of good. So after the first contribution of introducing the USR data set, they try to propose different the USR metric. So basically, USR metric consists of 2 parts. One is the mask language modeling, the MLM metric, which is used to evaluate the understandability and the naturalness of the response. What they do is basically they fine-tune a RoBOTA-based language model on the personal chat or topical chat data set. Then after that, they try to compute the log probability of each mask word. For example, here, given the context, how are you? Then the original, for example, the general response is I am okay. So they mask 1 word at each time. Then use the fine-tuned RoBOTA to give a score. For example, we first mask I, then we try to see what is log probability of the model to predict I, and so on and so forth. Then after that, we add them up, then we negative the sum. So means that because usually the log probability score correlate in a negative way with the human score. So that's why we negative here. And the second submatrix of this USR metric is the dialogue retrieval matrix. Basically, it's adopted to evaluate the other 3 fine-grained quality, the maintaining context, interestedness, and using knowledge. So it actually, the metric relies on the contextual information to distinguish the original response from the random ones. So actually, it's kind of similar to what Ruber and the other MOD are doing, but they just adapt this task to evaluate the different qualities by manipulating the context information. So the first setting is like context consists of both the dialogue history and the fact, and they intend to use this information to tell whether to train the matrix whether the response is maintaining the context, as well as whether the response is interesting or not. The second setting is they just introduce the fact into a context without the dialogue history. So they use this kind of setting to train models that to evaluate the using knowledge dimension. So after the introduction of each submatrix, so we need to in a way to combine them together so as to, for example, if we want to evaluate the overall quality, so we need some mechanism to combine the submatrix score. So here basically the matrix here basically tells what the human thinks the importance the human gave to each fine-grained matrix with respect to the overall impression. So it's like for this A1 annotator, he thinks that there is a 0.43 importance in terms of interestedness with respect to the overall. So the contribution of the interestedness dimension should be greatest, but there are other human that thinks that like this A4 annotator, he thinks that the naturalness of the response should be more important. And so we can see that the human actually have different perceptions of what contribute the most to the overall quality of the dialogue. So how do we combine the metrics given that they are like different perceptions? So in general, we just what the authors did is they train a regression model, with the human annotated data. So that they try to for each dimension, they based on the training method, the data-driven method, they just obtain one weight and use the weight to combine the matrix. Okay, so after introducing the matrix details, we shall look at the performance of the matrix. So basically, the performance is evaluated by the Pearson or Spearman correlation of the matrix score and the corresponding human evaluation score along the different fine-grained dimensions. So we can see here the US bar or its submatrix kind of outperform the best reference-based matrix across all the dimensions, like the BERT score, which is famous reference-based matrix. And also we can see that the both submatrix like the USR MLM and the USR DR actually perform as expected, because the USR ML are designed for naturalness and understandable. So we can see in the US, so we can see that the USR ML perform well on the corresponding dimension, and the USR DR performs well on the maintaining context and interestedness and use of knowledge. However, we can observe that after combining them, for example, the USR, if we combine the USR DR and the USR MLM, the performance for some dimension drop, and it is actually far from very perfect correlation, because perfect correlation is 1. So they are kind of not very high here. So there are still significant room for improvement. So let's dive into the next representative example, which is the D-score. So one major issue with USR is that they treat the evaluation of individual dimensions as independent. So this means that there's no correlation at all between different dimensions. But however, in previous studies, we found that human judges actually do not evaluate different aspects in a completely independent manner. For example, in the figure here, the adequacy and the fluency dimensions, basically the human score of adequacy and the human score of fluency are actually they correlate in a very significant manner. So these dimensions are not actually completely independent. So we need to, like a way to capture such dependence among different dimensions. So that's why that's motivation of this D-score paper. They basically adopt the multitask learning to learn a holistic matrix that can evaluate the different dimensions such as naturalness, response appropriateness, coherence, and consistency. So since this score is similar to the other matrix, it's kind of based on self-supervised learning. So we don't use human annotation to train this model. So we need to design different pretext tasks to handle each of the dialogue tasks. Each dialogue aspect. So the first pretext task is to discriminate the original response against the random utterance, which is similar to the previous other matrix are doing. So these kind of pretext tasks aim to capture the response relevance or whether the response is appropriate with respect to the context. And the second pretext task is shuffling order of the utterance. So for example, we have the preceding utterances as the succeeding utterances and the current utterance. We just swap the order of the current response with one utterance in the preceding context or one utterance in the succeeding context. So normally this ordering, shuffling is try to capture the coherence of the responses. So the third one is we try to rely on the third pretext task. We try to rely on the natural language inference task. So basically, we want to show that whether the current response is entailing the prevailing context or it's contradicting the context. And the last task is a language modeling task, which is a standard. We try to evaluate the naturalness of the response. So it's a standard language modeling objective. Then after that, with these 4 pretext tasks, we try to rely on multitask learning to simultaneously train a model that learn all these pretext tasks. Then the input to the model is just a sequence of utterances, and we use the robotic encoder to encode both the context to encode all the utterances. So for example, this preceding utterance context and the current response through this robotic encoder. So it's like one sequence of embedding vector. And here we concatenate the current response and the succeeding context. This is another sequence of embedding vector. Then through an additional BioSTM layer is to further capture the sequential interactions of all the words. Then after that, we use alignment layer to transform these vectors into a single score corresponding to each dimension. So we see that. So here we look at the performance of the D-score. So here is like a Spearman level, system level Spearman correlation. So we can see that actually compared to to USR, here should be USR. Here is the matrix fusion. So this score actually achieves the highest correlation across almost all the dimensions. And in terms of average, it's like the USR can achieve like is 0.279, but the D score is like obtains almost 0.563 correlation score. So this means that this showcases the advantages of multitask learning. So let's dive into the next matrix. So this matrix is called MDD-Val. So basically actually observe this matrix is published in IEEE 2022. So we observe that all the existing training-based metrics, they act kind of like a generalized skill to evaluate dialogues across multiple domains. This means that some metrics perform well on a particular domain, but the other metrics may perform well on a different domain. As we can see here, the DEB and the grade metrics, which are trained on the daily dialogue domain, they generally perform well on daily dialogue benchmarks. But the USR, which are trained on the topical chat domain, they just perform well only on the topical chat domains, topical chat benchmarks. So we want to design a matrix actually that work well across different data sets or different domains. So how do we do that? So basically so there are two possible solutions. So one is we can recruit the humans to write multiple relevant and hard negative responses given a dialogue context. And this dialogue context can come from different domains like personal chat or daily dialogue. But this type of method to collect a large-scale multi-domain training data is very expensive and kind of difficult to scale. And there are also other people that rely on data augmentation techniques to mimic the human written way of collecting data, but such way is the quality. There is no quality control. There is a potential to introduce low quality data, such as the false negatives. For example, some generated response may be correct given the context, but if we use augmentation, it will treat it as a negative response. So it's kind of harmful to the model training. So how can we design? How can we combine the advantages of both human method, which is high quality, and the data augmentation techniques, which can enable us to collect a large scale data? We rely on this semi-supervised learning method. It's called self-training. It's basically we apply a teacher model, then trained with high quality labeled human data. Then we use the teacher model to create synthetic labels for the unlabeled example that are generated with the data or the data augmentation techniques. Then after that, we combine the pseudo label data and as well as the human label data to train a student model to perform the task. So the step one of this pipeline is first to train a strong teacher classifier, which means that we fine-tune a Robota encoder on a daily dialogue ++ dataset. This dataset is a high quality human generated dataset. So it contains a dialogue context and human return relevant response adversarial, and this random response is randomly sampled from another conversation. So the quality of the data set is good, so we can use it to train this teacher model. So basically the accuracy of this teacher model is able to discriminate, is able to achieve 80% of accuracy to distinguish all these different type of responses. So the step two is to perform data augmentation to obtain a large-scale multi-domain data. So here is the list of strategies. So firstly, in order to obtain the perform data augmentation, we need the source data. So for source data, we sample dialogue context and response from this human dialogue from the previous mentioned 4 different data sets like daily dialogue, person chat, and perceptual dialogue, and the topical chat. Then after that, we can do back translation of the dialogue response so as to obtain the positive samples. And we also can do mask and fill strategy, means that we randomly mask some words in the response, and then we use the GPT model to generate a mask language model to predict the words, to auto denoise the response. So then use this kind of strategy as to generate the adversarial response. Then thirdly is the random sampling, which is similar to what we mentioned before. And of course, we can also rely on like large-scale pre-trained chatbots such as DialogGPT and BlendBot. They are very nowadays. They can generate very human-like response conditioning on the context. In this way can also generate some relevant and adversarial responses. Then of course, following MAU-D, we have the syntactic perturbations to generate the negative responses. So step 3 is actually the quality check step. Sorry, it's a pseudo labeling step. So we use the teacher model to assign soft labels to the augmented unlabeled data obtained in step 2. Then the soft label is a probability distribution of the 3 classes like random, adversarial, and relevant. Then we adopt a quality check step. So like we keep the data that teacher is most confident about. For example, it assigns the probability. It thinks that the response is relevant 70% of the time. So we keep the data. So we filter out those low confident samples. So in this way, I obtain like a large scale pseudo labeled data set. Then after that, in step 4, we combine this pseudo labeled data set and the original daily dialog process, which is the human labeled data set, to train a student model, which is the same architecture as a teacher model, but initialized with only the Robota, the initial weighting initialization. So we train the model with 3 different losses. One is the standard cross entropy loss to tell do the classification task. The mask language modeling loss, which is to adapt to enable the student model to adapt to the the pseudo label data set. Then the QL divergence loss, which is which is a common technique for self-training to regularize the training process. So we introduce some noise to the response, and also as well as the original response. We try to force the model to make the same prediction to the noised version and the original version. So then we minimize the QL divergence. So we train this model in an end-to-end manner. So that's basically the whole all the procedure of MDD volumetric. So the performance, in terms of performance, we can see here the MDDS is the final student model, and the MDDT is the teacher model, which is trained on human label data. And also we compare with DEB, which is trained on the daily dialog data, and the USL and the USR here, which we introduced previously, and D-score, which we also introduced the D-score. So we can see here in terms of the performance across on different benchmarks from different domains, the student model performs well. The MDD student model performs well across different domains than both USR and the D-score, as well as the teacher model here is 0.37, and here we obtain 0.47. So basically, the takeaway message is that in order to train this multi-domain generalized model, we need to collect high quality data. So we can always rely on this semi-supervised method to collect large scale data set for training our models. So now basically that's the end of the turn level matrix. Does anyone have any questions?